Similitude. This is using models to experiment to gain an estimate of a prototype's reaction. So we can do that with geometric similarity, where the model and the prototype are identical in shape, but they differ in size. Like say a 1 in 10 scale means that the model is 1/10 the size of the actual prototype. Or the length ratio is the length of the model over the length of the prototype. There's also kinematic similarity. This would be in addition to geometric similarity, where the ratio of velocities in all corresponding points are the same. So our velocity ratio would be the velocity of the model over the velocity of the prototype. In addition to kinematic similarity, dynamic similarity needs the corresponding forces to be the same. Let's talk about some of the ways that these similarities can be compared using dimensionless variables, like Reynolds number, R. Reynolds number is usually used in conduit flow where gravity doesn't really matter because the conduit is full. Therefore, the significant forces influencing Reynolds number are inertia and viscosity. Or if we're talking about like a submarine, friction and inertia. Reynolds number then is represented by the length, the velocity and the density of the liquid, and the viscosity. Or we can put that in with kinematic viscosity, V over nu. Another example, so if we have gravity and inertia forces like wave action on a ship are the major influences, we're going to want to use Froude number. Which is equal to velocity divided by the square root of g times L. If compressibility is important, then we need to use Mach number, where Mach number is equal to velocity divided by the square root of sound, or velocity divided by the bulk modulus over rho. And last, we have Weber number. Weber number comes into play when surface tension is very important, like bubbles. Weber number is going to be velocity divided by surface tension over density and length. So if we have an airplane traveling in the air at 150 meters per second, and the air temperature is 10 degrees Celsius, what does the density of the air in the wind tunnel need to be if we want a 1 in 5 scale with an air temperature of 25 degrees Celsius? To do this, we need to satisfy the Reynolds number and the Mach number. So if I go to Appendix A, I find that the viscosity for my prototype, the actual airplane, is 1.76 times 10 to the negative 5 Newton seconds per meters squared for 10 degrees Celsius. And my model will have a viscosity of 1.83 times 10 to the negative 5 Newton seconds per meter squared when the temperature is 25 degrees Celsius. I also do a quick temperature conversion, and 10 degrees Celsius is equal to 283 Kelvin, and 25 degrees Celsius is equal to 298 Kelvin. Now I wanted that viscosity because if we go to Reynolds number, because what we're looking at is having the Reynolds number of the prototype equal the Reynolds number of the model, And the equation for Reynolds number is rho v L over mu. And the problem statement is asking for the density of the model. So if I clean this up and solve for density and pair up my values, the density of the model is going to equal to the density of the prototype times the velocity of the prototype over the velocity of the model, the length of the prototype over the length of the model, and the viscosity of the model over the viscosity of the prototype. Okay, we've been given the 1:5 ratio, so we have the length 1, 1 and 5. Okay, we just looked up our two viscosities in the appendix, so we have that. And we were given the velocity of the prototype is 150 meters per second. What we don't have is the density of the prototype or the velocity that the model needs to travel at. I can use the ideal gas law to solve for the density of the prototype because I've been given all that information. Density is equal to pressure over the gas constant times temperature. And we were given a pressure of 100 kilopascals. Our gas constant, again from Appendix A, is 287 joules per kilogram Kelvin. And then our temperature is 283 Kelvin, making our density 1.23 kilograms per meter cubed. So now we have the density of the prototype. So let's use Mach number to get the velocity. The Mach of the prototype needs to equal the Mach of the model. And Mach number is velocity over the speed of sound. And we were told, because this is an ideal gas, that our speed of sound equation can be represented by the square root of the absolute temperature. So that means, rearranging all of this and plugging in my absolute temperature, that the velocity of my model, so this will equal to 150 meters per second times the square root 298 Kelvin divided by 283 Kelvin, which gives us a model velocity of 153.924 meters per second. So that's how fast our model needs to travel. So do we have everything? I think we do. Let's plug it in. Density of the model is equal to the density of the prototype times the velocity of the prototype over the velocity of the model times my ratio times my viscosities, and we calculate a required air density for our modeled situation to be 6.23 kilograms per meters cubed. So in order to determine the formation of waves around an obstruction of a river, we're going to make a model of the river, 1 in 10 scale, and determine the speed of the water for the model. Now this is a river, so open channel, so Froude number is going to be the controlling value here. So Froude number is velocity over the square root of gravity and length. So we're going to have the velocity of the model, gravity, and the length of the model will be set equal to the prototype. Of course, gravity is going to stay the same. Both the prototype and the model are going to be on Earth. So the velocity of the model needs to be a ratio of the length of the model over the length of the prototype times the velocity of the prototype. Therefore, the velocity of the model is going to be the 1 in 10 scale that we were given times that 6 feet per second velocity we were given for the actual river. And that gives us a velocity of the model of 1.897 or 1.90 feet per second to run in our simulation.